7 minutes ago, the Euclid Space Telescope transmitted a new batch of images to Earth. And within those images, scientists have identified structures so unexpected, so fundamentally disturbing, that multiple research teams are now questioning whether our current understanding of cosmic evolution can remain intact. What you are about to see is not another collection of beautiful galaxies. These are photographs that reveal anomalies in the fabric of space itself, patterns that should not exist according to our models, and evidence of forces acting on scales we were not prepared to witness. Tonight, I am going to show you exactly what Euclid captured, why these images are being called terrifying by astronomers who have spent their careers studying the cosmos, and what it means that the universe appears to be behaving in ways we explicitly did not predict. Stay with me because what scientists are seeing in these images may force us to rewrite fundamental assumptions about how reality is structured. The first image in this latest release shows a region of deep space roughly 400 million light-years from Earth. At first glance, it looks like a standard wide field view, thousands of galaxies scattered across the frame, glowing softly against the darkness. But when researchers applied Euclid's gravitational lensing analysis to this image, something deeply unsettling emerged. The distortions in galaxy shapes, the subtle warping of light that reveals where dark matter is concentrated, are not matching the predicted distribution. In multiple locations across the frame, dark matter appears to be clumped in configurations that standard cold dark matter models struggle to explain. These are not minor discrepancies. They are structural anomalies, regions where the invisible scaffolding of the universe looks fundamentally different from what simulations have been telling us for decades. The terrifying part is not that dark matter is behaving strangely in one spot. It is that this pattern is repeating across multiple regions of the sky. When scientists zoomed into one of these anomalous zones, they found something even more disturbing. A massive filament of dark matter stretching across tens of millions of light-years, but instead of being smooth and continuous as theory predicts, it appears fractured. There are gaps, breaks in the density that look almost deliberate, as if something carved sections out of the cosmic web. No known process in standard cosmology explains why dark matter filaments would fragment this way. They should be continuous structures shaped by gravity alone, gradually pulling galaxies along their length. But Euclid is showing interruptions, voids within the web itself, and galaxies that seem to be clustering around these breaks rather than avoiding them. This suggests that either our models of how dark matter behaves under gravity are incomplete, or there is an additional force at work that we have not yet identified. The second image released just minutes ago focuses on a galaxy cluster designated as EUCL-J0921, located approximately 2.8 billion light-years away. This cluster contains over 1,500 galaxies, and Euclid captured them all in a single frame with resolution so sharp that individual spiral arms and tidal streams are visible. But the shocking discovery came when researchers measured the gravitational lensing signature produced by the cluster. The amount of mass required to create the observed lensing effect is nearly 30% higher than what can be accounted for by the visible galaxies and the expected dark matter halo combined. 30%. That is not a rounding error. That is a missing mass problem on a scale that challenges the very foundation of how we calculate cosmic structure. Either dark matter is far denser in this region than any model predicts, or there is an entirely additional component of mass that we have no framework to explain. What makes this discovery even more unnerving is that EUCL-J0921 is not unique. Preliminary analysis of surrounding clusters in the same observational field suggests similar mass discrepancies. This is not an isolated anomaly. It appears to be a pattern a systematic underestimation of mass that could mean our understanding of how matter distributes itself across the universe is fundamentally flawed. Scientists are now revisiting decades of data from other telescopes, trying to determine whether this discrepancy was always there, hidden beneath lower-resolution observations, or whether Euclid is detecting something new, something that only becomes apparent when you observe the universe with this level of clarity. The third image is perhaps the most visually disturbing. It shows a region of the cosmic web where three massive filaments intersect, forming a node where galaxy clusters are born. Euclid captured this intersection in unprecedented detail, revealing not just the galaxies themselves, but the faint glow of intra-cluster light, stars torn from their galaxies and scattered into the space between them. But buried within this image is something that has left researchers genuinely unsettled. There are alignment patterns. Dozens of galaxies spread across millions of light-years, oriented in the same direction, their spiral arms and axes pointing along eerily similar angles. Statistically, this should not happen. Galaxy orientations are supposed to be random, influenced only by local gravitational interactions and their formation history. But Euclid is showing coherence across vast distances, as if these galaxies are responding to a large-scale field, something that is aligning them over scales where no known force should be able to exert that kind of influence. This is not the first time alignment anomalies have been hinted at in cosmological data, but Euclid's resolution makes the pattern undeniable. You can see it directly, galaxy after galaxy, tilted along invisible lines. Some researchers are suggesting this could be evidence of primordial magnetic fields, vast magnetic structures left over from the early universe that are influencing galaxy formation even now. Others are proposing even more radical explanations, including the possibility that we are seeing the signature of cosmic strings, hypothetical one-dimensional defects in space-time predicted by certain quantum field theories but never observed. If cosmic strings exist, they would exert gravitational influence in highly unusual ways, potentially aligning galaxies along their length. The terrifying part is that confirming this would require rewriting not just cosmology, but the standard model of particle physics itself. Euclid's infrared capabilities also revealed something in this latest batch that was entirely unexpected. Deep within one of the images, buried among thousands of distant galaxies, is an object that does not fit any known classification. It is not a galaxy, not a quasar, and not a star. Its spectral signature suggests it is extremely distant, possibly over 10 billion light-years away, yet it is emitting light in a pattern that resembles neither a steady source nor a transient event. The light curve is irregular, fluctuating in ways that suggest internal structure, but the object is far too small to be a galaxy and far too luminous to be a single star. Researchers are calling it a phantom source, a placeholder term for something they do not yet understand. Multiple hypotheses are being tested. It could be a gravitationally lensed background object, magnified and distorted into an unrecognizable form. It could be an entirely new class of astrophysical phenomenon, something that only becomes visible when observed with Euclid's unique combination of wavelength coverage and resolution. Or, and this is the possibility that no one wants to say out loud yet, it could be something that defies current astrophysical categories entirely. One of the most disturbing implications of these new images is what they suggest about the predictability of the universe. For decades, cosmology has operated on the assumption that the large-scale universe is statistically smooth, that while small regions might behave unpredictably, the overall structure follows reliable patterns governed by gravity, dark matter, and dark energy. Euclid is showing cracks in that assumption. The anomalies are not smoothing out as more data comes in, they are sharpening. The more clearly we see the universe, the less it resembles the simulations we have been running. This raises a question that strikes at the heart of science itself. If our models cannot predict what Euclid is observing, are we missing a fundamental piece of physics? Or are we looking at a universe that is inherently more complex, more chaotic, than our equations can capture? The fourth image in the release focuses on a nearby dwarf galaxy, barely 30 million light-years away, small enough to fit comfortably within Euclid's field of view. On the surface, it looks unremarkable, a faint smudge of stars with irregular morphology, the kind of galaxy that usually gets catalogued and ignored. But Euclid's sensitivity revealed something hiding in the outer regions of this dwarf, a faint halo of stars that extends far beyond the visible disk, and within that halo, structures that look disturbingly like tidal streams, long trails of stars being pulled away by gravitational forces. The problem is, there is no nearby galaxy massive enough to create those streams. The dwarf is isolated. There is nothing pulling on it. Yet, the streams are there, clear and undeniable. Either this galaxy experienced a close encounter with something massive millions of years ago, and we are only now seeing the aftermath, or it is currently being influenced by a dark matter substructure, a clump of invisible mass passing through or orbiting nearby, tugging stars into space without leaving any visible trace. This discovery adds weight to a growing suspicion among dark matter researchers. Dark matter may not be as smooth as we thought. Instead of forming simple round halos around galaxies, it might be clumpy, filled with substructures, dense knots, and wandering fragments that can gravitationally disrupt galaxies without ever being seen. If that is true, then the universe is far more dynamically chaotic than our models suggest. Galaxies are not just floating peacefully through space. They are constantly being jostled, twisted, and reshaped by invisible masses moving through the darkness around them. Euclid is giving us the resolution to see the evidence of these interactions for the first time, and the picture it paints is unsettling. Perhaps the most philosophically disturbing aspect of these new images is how they challenge our sense of cosmic stability. We think of the universe as ancient, vast, and slow-moving, a place where change happens over billions of years. But Euclid is revealing a universe that is constantly in motion, constantly being reshaped, where structures we thought were stable are actually fragile, held together by forces we barely understand, and vulnerable to influences we cannot see. The dark matter filaments are not permanent highways. They fracture. Galaxy clusters are not simple collections of mass. They harbor unexplained excess. Even empty space is not empty. It is threaded with fields, streams, and phantom sources that defy classification. The universe Euclid is showing us is not the calm, predictable cosmos we hoped to map. It is restless, intricate, and filled with phenomena that our current physics struggles to explain. And here is the truly terrifying part. These images were captured just minutes ago. The data has barely been processed. Researchers have only begun to scratch the surface of what is hidden in these frames. As more teams analyze the lensing maps, the galaxy alignments, the phantom sources, and the mass discrepancies, more anomalies will emerge. Euclid was built to answer questions about dark matter and dark energy. But it is becoming increasingly clear that its real legacy may be the questions it forces us to ask, questions we did not even know we needed to consider. What if dark matter is not a single substance but a spectrum of particles with different behaviors? What if the cosmic web is not just shaped by gravity, but by fields we have not detected? What if the universe at its largest scales operates according to principles we have not yet discovered? Scientists are not panicking, but they are recalibrating. Conferences are being scheduled. Data-sharing agreements are being fast-tracked. Theoretical physicists are dusting off old equations and proposing new ones. Because when a telescope like Euclid starts sending back images that do not fit the models, it means one of two things. Either the models are incomplete, or reality is stranger than we dared imagine. And right now, both possibilities are on the table. As you look at these images, as you absorb the weight of what they represent, remember that you are not just seeing distant galaxies. You are seeing evidence of forces that shaped everything, including the matter that eventually became you. The same dark matter halos that are clumping in unexpected ways. The same cosmic web that is fracturing in patterns we do not understand. These are the structures that gave rise to the galaxies, the stars, the planets, and ultimately life itself. We are not separate from this cosmic strangeness. We are built from it. Euclid is not just mapping the universe. It is mapping the boundary of human knowledge. And that boundary is shifting faster than anyone expected. If these images terrify you, good. That means you understand what is at stake. The universe is not waiting for us to catch up. It is revealing itself on its own terms, in its own time, with or without our permission. And all we can do is watch, analyze, and try to keep up. If you want to be part of that journey, if you want to witness the moments when science confronts the unknown and realizes it has more to learn, then subscribe. Share this with someone who still thinks the universe is fully explained. Comment with your thoughts, your questions, your fears, because this conversation is just beginning. The universe Euclid is revealing is not the one we thought we knew. And the most terrifying question of all is this: if we were this wrong about what we could see, what else are we wrong about in the vastness we cannot?